My name is Darby Dyar. I am the Deputy PI of VERITAS and the co-lead on the VEM instrument. My current affiliations are with Mount Holyoke College, where I am in the Department of Astronomy, and at the Planetary Science Institute, where I am a senior scientist. I would say that the VERITAS mission is going to give us the radar, topography, interior, and surface information we need to facilitate eventual landing on Venus, and also to greatly enhance our understanding of how planetary bodies form when they are terrestrial bodies. We've been lobbying for a Venus program, actually, just sort of like the Mars program. And as part of the Mars program, for decades now, we've been saying we want to go to Mars because we think that's the place where life, the only other place in the solar system where life is likely to have evolved. In the course of that, we've discovered two things. First of all, that Mars only had surface water for about 300 million years. And second, meanwhile, we discovered that Venus probably had surface water for 3 billion years. But I now believe firmly that we are more likely to find life or evidence of past life on Venus than we are on Mars. We need to go there. We need to look at the old rocks on the surface and see if we can find out anything about what happened during those 3 billion years. That's going to take eventually a lander, but before you can send a lander, you have to have better topography so that you know where to send the lander. And we currently have better topography for Pluto, which isn't even a planet, than we do for Venus. So, and we don't even know what the rocks are on Venus. So there's just so much we need to know about Venus, and VERITAS is sort of the first foundational step. Tell us what the topography is, tell us what the interior looks like, tell us what kind of rocks are on the surface. And once we have that information, then we're going to give birth to a whole new generation of Venus science and hopefully Venus scientists. My role as the Deputy PI is basically to support Sue Smirkar in any possible way. So anything that I can do to help Sue do her job, I will do. And more specifically, Sue is trained as a geophysicist and I'm trained as a geochemist. And so it sort of divides naturally that Sue knows and understands in great depth all of the stuff around the radar, all the information about VISAR. Whereas because I'm a spectroscopist, the area of expertise is more appropriate to understanding VEM. And so I sort of tend to focus on the things involving VEM. The amazing team at DLR is building the VEM instrument, but calibrating the VEM instrument and understanding how to relate data that we acquire from orbit to data that we acquire in the laboratory it is the domain of both engineers and also computer scientists. And in that role, I am the computer scientist who uses something called calibration transfer to try to understand how we relate the data we acquire on Venus to the data that we've acquired in the laboratory. And in the meantime, we are running many, many rocks in the laboratory under Venus conditions to try to understand what different rock types are going to look like under Venus conditions. And ultimately, what we want to do is make a true geologic map of Venus. We have currently geologic maps of Venus, but they don't have rock types on it. And there are all of these questions that are predicated on understanding the chemistry of the rocks. And so what we've set ourselves to do as a science goal for VERITAS is in some ways extremely simple. It's how do we tell the difference between the high iron basaltic rocks that indicate simple volcanism and the high or the low iron, high silica rocks, which would indicate more complicated surface processes, possibly the presence of water when they formed, and possibly some kind of plate tectonics or more dramatic modifications to the surface of Venus. So that's a really important distinction for us to make, and it's the reason why it's one of the most important goals of the VERITAS mission. So the surface of Venus is both hot and very high pressure. And to give you a way of relating, well, let's start with why that happens. The surface of Venus is hot and dense and overbearing pressure because of the CO2 atmosphere. So what happened was that Venus at some point probably had liquid water on its surface. Over a period of time, as the sun got brighter in our solar system, the temperature at the Venus distance around the sun got hotter and hotter. That, in combination with the solar radiation from the sun, picking off things out of the Venus atmosphere, picking off the hydrogen in particular out of the Venus atmosphere, what got left behind was the other big volatile that comes out of volcanoes, which is CO2. And so over a period of time, Venus's atmosphere got thicker and thicker, And of course, you know from your studies of the greenhouse effect on Earth that CO2 is a greenhouse gas, and it allows energy to get in but not to escape. And so the surface of Venus gradually heated up over time and got more and more high pressure. So to put that in perspective, think about what your oven looks like when you turn the broiler on. So when we get to Venus, that's probably what, if you were to take a normal picture, that's what it's going to look like. It's very hot. So I would say probably 20 years ago, I started thinking about using machine learning to understand spectroscopic measurements, and some of my other lines of research involve this much more intimately. So a whole branch of my research is about studying tiny samples that are returned by extraterrestrial missions. So it started out studying meteorites, right? Because those are essentially randomly delivered to Earth, right? They call meteorites the poor man's space program. We obviously want the largest possible data set to train the machine learning models on. And making the measurements at DLR is not a trivial process. If they really hustle, they can get 2 samples run in a day, but more typically it's 1 sample a day. And so when you do the math and you think about all the other priorities that they have going on at DLR, I'll be lucky if I get 100 spectra per year. So, when you view it like that, 7 years doesn't seem that long. We only have about 100 now. So, if we had 800 when we launched, that would be great. So the way we study rock types under Venus conditions is, in theory, you would think that we would want to study them at 460 degrees under 90 kilobars of pressure. But it turns out from past studies, we know that the pressure doesn't actually shift any of the spectral peaks that we're interested in very much. So luckily, we don't have to actually reproduce the pressure in the laboratory, which is a huge relief because that experimentally becomes quite formidable. However, you do have to heat the rocks up because it's intuitively obvious that a rock that's at 460 degrees is going to emit heat in a different way than a rock that's at 30 degrees C. And so the laboratory at DLR was specially designed, and they started working on this 15 years ago, more than a decade ago. It's a chamber that's evacuated, and it has little cups, and the cups are heated from underneath. And so we create these special slabs of rock. We put them in the cup. It gets heated from below, and we wait for them to start to glow, and then we take our spectra. Oh, well, to me, the projects I'm most excited about are actually involving technology of transportation. My son is a transportation engineer, and what he does is incredibly fascinating to me because he's looking at the big picture of what will happen as the U.S. transitions to electric cars and what will happen to the infrastructure and how politics are intertwined in the whole bureaucracy of how we're going to enable transportation in the future in this country. And so to me, of course, this also, is tangentially related to what I do, right? Because at some point, spacecraft are going to transition into different forms of energy. But I find that both, something that hits very close to home, and also the evolution of non-traditional transportation is a thing that I find pretty exciting.